parallel axis theorem. All right, let's begin. So by the end of this video, we're actually going to do an example that you see here. We're going to try to go from this rotational inertia to this rotational inertia. Okay? All right. So when to use the parallel axis theorem? There's two requirements. You first need to have the axis of the rotational inertia of your initial system. So either the problem gives it to you or you solved it somewhere along the way. And the second thing that you're looking for, and this is the most important part, okay, the problem shifts the axis of rotation to a new axis of rotation. So here's I guess the best way to do this is by looking at an example here. So this is example one. Okay, so let's say you have a rod, right? So I'm going to use my pencil here. I'm going to say the axis of rotation is right in the middle. Okay, so I'm going to pivot my pencil back and forth. Okay, so what that looks like is, so here's my rod, and my axis of rotation is right there. Okay, now that's situation one, and you use the parallel axis theorem when the problem says, hey, what if we were to shift the axis of rotation from the middle to, let's say, the end here? And now we have a different axis of rotation, and what that would look like here in my drawing would be the following. So this is axis of rotation. I'm going to put a little subscript 2 for my second one. Okay. The things that you're looking for is just that, right? You have a rotational inertia, and you are trying to find the new rotational inertia if you were to shift the axis of rotation. So the parallel axis theorem does have a formula, and that is I is equal to, so this is the I nu, all right? It's equal to I when it is about the center of mass, okay, so right there in the middle, plus md squared. And you might see this written in different ways, where it's like a d or an L or an R, but the important thing is that the d is the shift from your center of the object to a new axis of rotation. So that would be the d that's being squared. Now, to see where we get the name parallel axis theorem, right? So the idea is, hey, this axis of rotation here is parallel with this axis of rotation here. And so if you're shifting the axis of rotation in a parallel fashion, what is your new formula? Okay, and so this is the base formula that we can use. Okay, let's try this. So we'll just use this example here. We know that the I about the center of mass, according to our chart, I believe it's a 12th. Yeah, 1/12 ml squared. Okay. And we know that the I nu, so we're trying to get to a point where we get 1/3 ml squared. All right. So for the way that this formula works, the mass of the object is still m. And what we did is we shifted the axis of rotation, this location d. So let's think about this in the context of the problem. The rod itself has a length of L, so that must mean that d is equal to a half of that L. So if I do 1/2 L squared here, right, we get a 12th ml squared plus a 1/4 ml squared. And what we want to do is we want to add a 12th to a 1/4. Don't know how to do that at the top of my head, so I'm just going to show you the algebra. So this would be 3/12. 1, 4, 8, 12. Yeah, 3/12 ml squared. So this gives us 4/12 ml squared. And if we reduce that, we would get a 1/3 ml squared. So the new axis of, the new rotational inertia will be 1/3 ml squared. And the cool thing here is if we look at the chart, we are in fact correct. All right. So that's how we went from rod about the center to rod about the end. And we just went over when to use the parallel axis theorem. Okay, so the more difficult problems that you might see is it's just going to combine like two separate skill sets. So in another video, I go over, hey, what if the problem gives you, let's say, lambda, right, which is the length of the object divided by the mass. Okay, so we're going to have to use a little bit of, that's the reverse, the mass of the object divided by the length. And so we would have to use a little bit of calculus to see how to find the new I. Okay, so that might be the only different way of approaching this problem where you're not given the I, but you have to find the I and then do the parallaxes theorem. But the formula for the parallaxes theorem is the following. Okay, so have that there, box it, star it, and be ready to uh, tell me what that is from memory. Put that there, memorize. All right, see you next time. Bye bye.